We're surrounded by all this amazing high-tech stuff, from electric cars to smart appliances, but have you ever stopped to think about what's really making it all work? Deep down, hidden from view, there's this tiny electronic component, a super powerful switch that's controlling massive amounts of energy. So let's dive in and figure out what this thing is.
Right, so what is this hidden hero? What's the one thing that connects, say, the insane acceleration of an electric car, the raw power of a bullet train, and even the super precise heat on your induction stove? Well, it all comes down to this really clever piece of engineering called the insulated gate bipolar transistor, or for short, the IGBT.
And believe me, its reach is absolutely staggering. I mean, this thing is the brains behind the brawn in your EV. It's in the inverters that turn solar and wind power into something we can actually use in our homes. It's in the power supplies that keep massive data centers from ever going dark. Basically, if you have something that needs to control a lot of power precisely and efficiently, you're going to find an IGBT in there.
Okay, but a device this cool didn't just pop into existence, right? To really get why it's so special, we have to go back and look at a classic problem. Think of it as a tale of two transistors and the huge dilemma engineers were facing. For decades, they basically had two main tools for switching power, and honestly, neither one was perfect for the job.
So on one side, you had the power MOSFET, and a great way to think about this is like a super fast light switch. It's really easy to control. You just give it a little voltage signal and bam, it's on or off. The problem? Well, just like your light switch at home, it can't handle a massive amount of power. Then on the other side, you had the bipolar transistor, the BJT. Now this thing was like a giant floodgate on a dam. It could handle enormous amounts of power, but, and it's a big but, it was slow. And it took a ton of energy just to open and close that gate.
And this chart, this really lays it all out, doesn't it? You can see exactly what the engineers were up against. They wanted the awesome current handling ability of the bipolar transistor, but they needed the easy control and the high speed of the power MOSFET. The mission was obvious. They had to create some kind of hybrid, something that gave them the best of both worlds.
Now, the idea for this hybrid switch had been floating around since way back in 1968. But for years, this brilliant concept had a fatal flaw. And that brings us to our next big chapter, teaming the latch-up problem. This was an issue so bad, it would literally cause the devices to destroy themselves. It almost killed the entire project.
This timeline really puts that struggle into perspective. Just look at this. The basic components, the bipolar transistor and the MOSFET, they were invented all the way back in 47 and 60. The idea for combining them came in 68, but it wasn't until 1984 that researchers finally figured out how to make it reliable. Almost 2 decades, and it all came down to solving that one single devastating problem. And the sources on this are crystal clear about how bad it was. I'm talking fatal device self-destruction. Yeah, this wasn't just some minor bug. It was a catastrophic failure that made the early versions totally useless and frankly dangerous for any real-world use.
So what is this latch-up thing anyway? Well, let's go back to that light switch analogy. Imagine you flip the switch on, and then it gets stuck. It's just permanently on, and you can't turn it off no matter what. That creates a short circuit. A massive uncontrolled flood of electricity just rushes through and poof, the thing instantly overheats and burns itself out. That, in a nutshell, is latch-up.
So the real breakthrough, the aha moment, wasn't about trying to stop the latch-up once it started. People had tried that for years and failed. No, the genius idea was to design the device so it could never draw enough current to trigger the latch-up in the first place. By tweaking the internal design, they basically built in a safety mechanism. It's like putting a governor on a car engine. It just won't let it go into the red zone. Problem solved. Okay, so with the latch-up problem finally licked, the IGBT was ready for the big time. But even a hero has to play by the rules. And that brings us to the safe operating zone. Because to use one of these things safely, engineers have to know its limits, and more importantly, respect them. And that rulebook is officially called the Safe Operating Area, or SOA. This is a super important concept for any kind of power electronics. The SOA basically defines the exact boundaries, the specific mix of voltage and current where the device can work without, blowing itself up. You stay inside those lines, you're good. You step outside, you're asking for trouble. And what's so cool is how engineers actually visualize these limits. This chart here is basically a treasure map of the IGBT's power. On the vertical axis, you've got current, and on the horizontal, you've got voltage. As long as the combination of the two stays inside that colored area, under the line, you're golden. But the second your application pushes it outside that safe zone, well, that's when things get exciting in a bad way. And this rulebook, it's not just one page. It's got different chapters for different situations. There's a set of rules for when the device is on, another for when it's turning off, and even a special set of rules for how to survive a direct short circuit for just a few millionths of a second. It's that kind of deep, detailed understanding that makes modern IGBTs so tough and reliable. So there you have it. After decades of work and one brilliant breakthrough, the IGBT was finally born. And that brings us to our final section, powering our modern world. Because honestly, the impact of this one little component, it's been nothing short of a revolution in how we control electricity. And the numbers really tell the story. Just look at this market data from back in 2010. Even then, the IGBT had already grabbed more than a quarter of the entire power transistor market.
It totally pushed its ancestor, the BJT, to the side and carved out this huge essential space right next to the MOSFET.
And this number is exactly why. An IGBT can handle a power density of over 500,000 watts per square centimeter. That's more than double what the older transistors could handle. That incredible ability to pack so much power into a small space is what makes all the smaller, lighter, and way more efficient electronics in cars and factories possible today.
So the IGBT was this brilliant hybrid, right? It solved a huge engineering puzzle for its time. But technology never ever stands still. As our world goes more and more electric, demanding even crazier levels of efficiency and power, it leaves you wondering, doesn't it? What's the next big thing? What innovation is coming after the IGBT? What's going to be the next unseen power switch that completely reshapes our future? Thanks for joining us.